Right, so moving on to the physical chemistry one. So they have given a reaction, AB and AB react with AB reacts reversibly to give C and D, and it's elementary in both directions. So you see here, you can think about your rate reaction because they have given it is elementary in both directions. So you can think about writing a rate equation for the forward and backward, and was carried out at 25 degrees Celsius. Initially, the reaction mixture was made by dissolving zero point 0.1 mole of A and zero point 0.1 mole of B in distilled water, and the volume total is given. So the total volume is 100 cubic centimeter, and the variation in the concentration of A is given. So the first point that I have to make here is don't misunderstand this with a rate curve, because this is not a rate curve. Okay, rate with time, because some people get lost here. In fact, some students in the last year also, they thought this curve is similar to here. This is a rate curve that you obtain from this concentration profile when you get the gradient. For an example, the concentration difference over time difference, when you divide it, so you get the gradient. Basically, that means the concentration difference over time difference, which is the rate. So at each point, you get the concentration difference and the time difference, then you write in a different plot, then you get the rate versus time. Okay, but here, don't forget, this is concentration profile with the time. In fact, here, this is the concentration variation of A. Okay, so we will go through this question a little bit. So this is concentration. So the concentration of A starts at 1 MOLDM minus 3. So we will check, is it true? Because the amount of A used is 0.1 mole. So 0.1 mole divided by the volume, that is 100 into 10 to the power minus 3 decimeter. So it is again 0.1. Yeah, so it is 1 M. This will be decimeter. So this is 1 M, that is true. So it start with 1 M. And B also will be starting from 1 M because they have used 0.1 moles of B, same in the same volume. So the concentration of A and B at the beginning will be 1 M and 1 M. So no problem in that. And you see here the concentration drops, and at the end of 4 minutes, right? So at the end of 4 minutes, you can see there is no change in the concentration of A, which should give you the idea at the end of 4 minutes, this reaction is become equilibrated. That means the equilibrium is achieved after 4 seconds, because you know at equilibrium, the rate of the forward reaction and the rate of the backward reaction becomes equal, and there is no change in the specific concentration. Okay, so that is what you can get from this particular graph. Other than that, after 4 minutes, in fact, you can see here the concentration is just in between 0.5 and 1. So this is around 0.75 based on the scale given. Okay. Right. First question. Calculate the amount of A in moles reacted during the first 4 minutes of the reaction. So basically, you see here, the concentration difference will be the amount that is reacted, right? So you can just calculate. You can just write down moles of A reacted will be equal to 1 minus 0.75, because that is the time after 4 minutes, and this is in concentration, but you can change that by multiplying with the volume. So this is 100 into 10 to the power minus 3 in decimeter. So MOL dm minus 3 to dm minus 3, so it will be cancelling out. giving you, in fact, this is a decimeter cube, dm cube to dm minus 3, so cancel out. So you can have your answer in moles. So it is 0.025 moles. Okay, so this is how you can obtain your answer. Would the rate of the forward reaction be less than the rate of the reverse reaction after 4 minutes? Explain your answer. So the simplest explanation I gave you, because after 4 seconds, you can explain the concentration of A does not change, which gives you the idea the equilibrium is achieved. Therefore, the rate of forward reaction is equal to the rate of backward reaction, and the rate does not change. Given that the rate constant of the forward reaction, K forward, is 18 something, calculate the initial rate of the forward reaction. So you know here, for this forward reaction, the reactants are A and B. So R should be equal to Kf, I would say, and concentration of A times 1 and concentration of B times 1. Why I took the orders as 1? Because they have given this is elementary in both directions. So I can take the stoichiometric coefficient. Then I know Kf, it is 18 something, 18.57. So you have to put the units here and then multiplied by the concentration of A and B raised to the power 1. So A and B at the beginning is 1m for A, 1m for B. So these are not going to change. So 1m to the power 1 and 1m to the power 1. So your answer would be this one. So put the unit for the rate of the reaction. It will be mol dm minus 3 per minute. Okay. And the next question, calculate the concentration of C and D at equilibrium and draw the relevant curves showing the variation of the concentration of C and D with time in the above graph and label them. So first thing is you have to find the concentration of C and D. So this is our reaction, right? So I will choose a different color now. So you see here after 4 minutes, so A, initially we have 0.1 moles of A, 0.1 moles of B. This is the initial case. And we have calculated after 4 minutes how much of A was reacted. So it is 0.025, which means at the end of the equilibrium, you have 0.075 amount of A, right? So it is like 0.1 minus X and 0.1 minus X. And here there are 2X is formed and here there is X is formed for C and D. And we already know what is the amount of X here. So X is 0.025. So we found that in here in the first question, the amount of moles that is reacted. Then you see here how much C is going to form. It's 2 times as X. So it will be like 0.5 moles of C and 0.025 moles of D. Okay, so you know the number of moles of C and D, so it will be no problem here to get the number of moles of C and D. Then what you have to do here is just divide by the volume, right, to get the concentration. So you can automatically find the concentration. So C concentration will be here. What is the amount of C? It is 0.5. So it will be 0.5 moles divided by 100 into 10 to the power minus 3. Right. So in a similar way, you can find for D, concentration of D, it will be 0.025 divided by the volume, 100 into 10 to the power minus 3. So these are very simple things that you should know. And when you find the concentration, so here 0.5 divided by 100 into 10 to the power minus 3 is 0.5. Okay, yeah, no problem in that. And here, when you find the concentration of D, you will still find it is 0.25, right? So you can understand the concentration of C after this time period 4 minutes, because this is at equilibrium that we find, okay? C, the concentration is 0.5, so the concentration of C should be here, somewhere around here. So it should increase because C is a product, so it should go like this, and it should be constant here after 4 minutes, right? It should be like this. Draw a single line. Okay, so it should increase like this and then constant. This is for concentration of C, right? And then for D, it is 0.25. So it is just in the middle of 0.5 and 0.0. So it is should be like this. And D is also increasing, so it should be like this. So this is the concentration profile for C and D. So this should be the graph that should be in your answer script. Okay, so you can draw it again. In fact, you don't need to draw it again because this is structured, say, question, so you can just plot here. Write the expression for the equilibrium constant Kc of the above reaction and calculate its value. So these all are just calculation, because you know Kc should be the product concentration over reactant concentration raised to its stoichiometric coefficient. So A and B, Kc will be C and D over A and B. The only difference here is C, you have a coefficient 2. So here there should be a power of 2. And you all know this concentration C and D is here. A and B after equilibrium, you know that it is A is 0.75. So B is also will be that. So I mean the concentration, then you can plug here those two values and you can find the Kc value. Okay, so these are very, very simple things that you can follow up. Right, so the next one is calculate the value of the rate constant K reverse of the reverse reaction. So this is one part that I have to tell you a little bit of more, because you have this equation where you find the Kc, right? So you find Kc, it is an equilibrium constant. But don't forget this K reverse is the reverse reaction rate constant. But there is a relationship that is given. So basically, when you have this Kc expression, right, the equilibrium constant expression, it typically gives you the rate constant of the forward reaction and the rate constant of the reverse reaction. Okay, so this is a general equation. Don't forget about this. And you have Kf already given, right? So it is 18 something. So this is 18.57. And you find K, equilibrium constant Kc, from this profile here. I will tell you the real value. So the real value, wait, give me a second. The real value is 1.11 into 10 to the power minus 1, for an example, in this particular question. So the only thing that you don't know is K reverse. So you can automatically find K reverse from this equation, right? So this is common equation for a reversible reaction like this. Right, question number 7. After reaching equilibrium, the volume of the solution was doubled by adding 100 cubic centimeter of distilled water. Predict the direction of the net reaction soon after doubling the volume of the solution by means of a suitable calculation. So the first thing that you need to understand here, after this process is done after equilibrium. So you know the concentration of these reactants and product at equilibrium. So this was like 0.75, 0.75, and this is 0.5, and this is 0.25. So based on that, you know what is Kc. Okay, so this is a condition where now you add 100 cubic centimeter to this equilibrated solution. So what is actually happened with the concentration of these reactants and products initially? So you have doubled the volume. So the concentration of A and concentration of B and concentration of C and the concentration of D all are going to get half of this equilibrium value, because this will be 0.75 at equilibrium. This was the same as the case, and this was 0.5 and this was 0.25, right? So after doubling the volume, all of this concentration will be reduced to half, right? So this is what initially going to happen. And then what you can do here is you can find a reaction quotient, RQ. So if you remember about R quotient, so do you remember that? I have explained this to before. So this is something like very similar to the equilibrium constant. So you can define as RQ, or this Q is an equilibrium constant that you find before the establishment of the equilibrium. Okay, so what you can do here, you can find this reaction quotient again just after the addition of 100 cubic centimeter of distilled water, because the concentrations, the initial concentration would be half here. So you will have like 0.5 over 2 to the power 2, 0.25 over 2, and 0.75 divided by 2 squared, for instance, because this is just a double factor, and you find RQ. So when you find RQ, you will see the RQ value for here is 0.056. Okay, so this is 0.056, but here when we find this Kc expression, it was 0.11. So based on this value, you can predict, because the temperature is still same. So this reactant quotient, this RQ value, should go from 0.056 to 0.11. So this value should go up to this, which gives you the idea this RQ value should gradually increase with time when it's reached the equilibrium. So how this RQ value is going to increase? There should be more and more products. This should be higher and this should be lower in order to have a higher RQ, which gives you the idea there should be more and more products that should be formed here, which gives the idea this forward reaction should favor. So you can write down here this RQ. Since RQ is smaller than the Kc at equilibrium, the forward reaction should favor in order to achieve this Kc value. So that is the simplest of the example, that explanation, in fact, that can give you guys. Okay, so get it done. Right, so moving on. Consider that the above experiment was conducted at a temperature lower than 25 degrees Celsius. How would this affect the rate of the reverse reaction? Explain your answer giving reasons. So it doesn't matter whether this is the reverse reaction or the forward reaction. When you drop down the temperature, the rate is going to reduce. That is one point that you have to mention here. The rate is going to reduce. What are the reasons? The reason is when you drop down the temperature, the kinetic energy of the molecules, which are the reactants here for the reverse reaction, C and D, will be reduced, and the collision rate will be reduced. That is one thing. And the second thing, when we are talking about the temperature, I explained to you before, we talk about two different things. One is the collision rate. The second one is you can explain when you drop down the temperature, the molecules, the fraction of molecule that exceeds the activation energy also going to be less now. Therefore, the rate is going to be lower. Okay, so you can explain those two cases. So this is another nice question I really like, because I saw some people are taking this curve as rate, and they are stuck at some point and then comes back and see this is the concentration, and they do the questions again and again. Okay, so this is not hard, but this is nice question, I would say.